Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into one of the most extraordinary mysteries in the universe: water. It seems simple, a clear liquid that flows, freezes, and falls as rain. Yet every drop holds an ancient story. The water in your glass may have once rippled across Martian plains, floated as mist above an ancient forest, or glimmered in the tail of a comet long before Earth was born. It is the most familiar substance on our planet, and still one of the strangest. It bends light, defies gravity, remembers the stars it came from, and carries the spark of life itself. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Allow your eyes to grow heavy, and let yourself flow gently into sleep. Let's begin. Every drop on Earth has been here for billions of years. Water never truly disappears. It only transforms, from vapor to liquid, from ice to mist, endlessly cycling through time. The same molecules that once drifted in the breath of dinosaurs now fall from modern clouds and flow through your veins. Each drop has journeyed through oceans, glaciers, roots, clouds, and the bodies of countless living things. Even the rain outside your window may once have been part of an ancient sea. The water that makes up your cells could have frozen at the poles a million years ago, or boiled from volcanic vents beneath primeval oceans. On a planetary scale, almost no new water is created or destroyed. It is Earth's oldest traveler, eternally renewed and recycled. Every river, every tear, every wave that breaks on the shore carries within it the memory of deep time, whispering stories of the world as it once was. The hydrogen in water was born in the Big Bang, before there were stars or planets. Before there was even light as we know it, the universe was filled with a glowing soup of particles. In those first few minutes after the Big Bang, protons and neutrons began to form hydrogen, the simplest and most ancient of all elements. Every hydrogen atom that now dances inside a droplet of water has existed since those first cosmic instants, untouched by time itself. It has traveled through nebulae, through stars, through the cold darkness of interstellar space. When it finally met oxygen billions of years later, it formed the molecule that would cradle all living things. To drink water is to drink the first breath of the universe, the element that made the stars and then, much later, made you. The oxygen in water came from dying stars. Oxygen did not exist when the universe began. It was forged later, in the hearts of stars that lived and died long before our sun was born. Inside their blazing cores, hydrogen and helium fused together under unimaginable pressure, forming heavier elements like oxygen. When those ancient stars reached the end of their lives, they exploded as supernova, scattering their oxygen-rich dust across the cosmos. That dust drifted and cooled, eventually becoming part of the clouds of material that formed our solar system. When oxygen met hydrogen, water was born. Every raindrop, every ocean wave, every misty breath is the echo of those long-vanished stars. You could say that water is the universe remembering itself, the ashes of creation turned to something gentle, something that moves and glimmers with the rhythm of life. Water exists in all known states of matter at once. In the right conditions, water can perform a quiet miracle. It can exist as a solid, a liquid, and a gas all at the same time. Deep within scientific laboratories and even in the natural world, there are fleeting moments where this happens, called equilibrium points. On a mountaintop or inside a vacuum chamber, tiny ice crystals can melt and evaporate simultaneously. The molecules shift between states so quickly that it is as if they refuse to choose one. This ability makes water unique among substances we encounter every day. It can move freely between worlds, becoming cloud, rain, snow, or steam, all depending on temperature and pressure. In this strange versatility lies the secret to life's persistence, the reason oceans breathe, and rain falls, and clouds drift endlessly through the ever-changing sky. There is a rare triple point where ice, liquid, and vapor coexist. Scientists call it the triple point, a precise balance where temperature and pressure align in perfect harmony. At this exact condition, water exists simultaneously as ice, liquid, and vapor. It is not a transition or a trick of light, but a true coexistence of three forms. In a laboratory, the sight is mesmerizing. A droplet that shimmers as it freezes and evaporates at the same moment. On our planet, such conditions are rare, appearing briefly in the delicate balance of high mountain air or at the edge of boiling springs. The triple point is a reminder that water does not obey ordinary rules. It dances between forms with grace, forever fluid in identity. In that small window of physics, water reveals its deepest secret, that it is not bound to one state but belongs to them all at once. Water expands when it freezes, and almost nothing else does. Most substances shrink as they grow colder, but water does the opposite. When it begins to freeze, its molecules arrange themselves into a crystalline pattern that takes up more space than the liquid around it. This strange expansion makes ice less dense, which allows it to float on water instead of sinking. The consequences of this single property are profound. If water behaved like other materials, lakes and oceans would freeze from the bottom up, trapping all life beneath layers of ice. Instead, the floating crust insulates the water below, protecting fish, plants, and ecosystems during winter. This quiet miracle of physics is the reason life on Earth survived through countless ice ages. Every frozen pond, every drifting iceberg is a living shield built from geometry and temperature, a reminder that survival often depends on the smallest quirks of nature. Ice floats because it's lighter than its liquid form. The surface of a frozen lake may look calm and heavy, but it is actually lighter than the water beneath it. When water freezes, its molecules lock into a lattice that spreads them farther apart. This structure reduces density, allowing the solid to rest gently above the liquid. The result is one of the most important and elegant designs in nature. Ice acts like a blanket, keeping the water below from freezing solid and protecting the creatures that live beneath. In the depths of winter, entire ecosystems owe their survival to this delicate balance. The floating ice reflects sunlight, slows evaporation, and shelters life from the cold. It is a fragile equilibrium that has shaped the rhythm of seasons for millions of years, quietly demonstrating that the laws of physics can be not only precise, but merciful. If ice sank, the oceans would freeze solid. Imagine a world where frozen water fell to the bottom of the sea. Each winter, new layers of ice would form at the surface and sink, piling upon the last. Over time, the oceans would turn to frozen snow, locking away the liquid water that life depends on. Our planet would become a silent sphere of ice, glittering but barren. Fortunately, water's molecular design prevents this fate. Because ice is less dense than liquid water, it rises instead of falling. The frozen layer at the top acts as insulation, keeping the depths warm enough for life to continue even through the coldest winters. Beneath the ice, fish still swim, currents still flow, and life endures. This single, delicate property of water keeps Earth alive, a narrow thread of chemistry that holds the difference between a frozen world and a living one. Supercooled water can stay liquid below freezing. Under the right conditions, water can ignore the rules of temperature. When cooled carefully and kept perfectly pure, it can remain liquid even far below the freezing point. This state, called supercooling, happens because ice needs a starting point to form, a tiny impurity or disturbance to begin its crystal lattice. In the absence of such a seed, the molecules keep moving, holding together as a liquid in defiance of expectation. The moment a speck of dust or vibration touches it, the entire mass can freeze in an instant, turning solid in a blink. Supercooled water exists naturally in high clouds, where droplets remain unfrozen until they collide with ice crystals or fall through turbulent air. It is a fragile reminder that the world around us is not rigid, but balanced on thresholds, always one breath away from transformation. Hot water can freeze faster than cold. It sounds impossible, yet under certain conditions, water that begins hot can freeze faster than cooler water. This rare and puzzling phenomenon is known as the Mpemba effect, named after a Tanzanian student who noticed it while making ice cream in the 1960s. Scientists have spent decades trying to explain why it happens, and the answer is still not completely understood. Part of the mystery lies in evaporation, which allows hot water to lose mass and cool more rapidly. Heat also changes the structure of hydrogen bonds, breaking apart clusters that later make it easier for the molecules to align into ice. Convection currents inside the container may also distribute temperature differently. The effect is delicate and inconsistent, yet it serves as a humbling reminder that even a simple liquid still holds secrets. In every experiment, water teaches us that nature never runs out of surprises. There is a state of superionic ice inside giant planets. Deep beneath the shimmering blue clouds of Neptune and Uranus lies a form of water that could scarcely exist anywhere else. Under pressures millions of times greater than those on Earth and temperatures hotter than the surface of the Sun, water transforms into something called superionic ice. In this strange phase, oxygen atoms form a rigid crystalline lattice, while hydrogen atoms move freely within it, creating a structure that behaves partly like a solid and partly like a liquid. It even conducts electricity, glowing faintly from the heat trapped inside. Scientists believe this superionic layer explains the unusual magnetic fields of these distant worlds. On Earth, researchers have recreated the phenomenon for only brief moments using lasers and diamond anvils. It may be one of the most alien substances in existence, a crystalline sea that shines invisibly within the hearts of frozen planets. Neptune may rain diamonds beneath its frozen oceans. Far below Neptune's calm, turquoise clouds lies a world of unimaginable pressure. In those crushing depths, methane molecules are squeezed so tightly that their carbon atoms bond into crystals of pure diamond. These glittering fragments fall slowly through layers of ice and liquid, forming what scientists poetically call diamond rain. Laboratory experiments on Earth have shown that such conditions can indeed turn methane into diamond under intense compression. If the same happens on Neptune, its atmosphere could sparkle with falling gems, drifting toward a dark ocean of superheated water. Some scientists believe those diamonds might even settle into vast layers or float like shining icebergs near the core. It is a vision both surreal and scientific, where physics becomes poetry. Deep inside a planet we can barely glimpse, storms of diamond may fall endlessly through seas that never see the light of day. Water molecules can form perfect hexagonal snowflakes. Each snowflake begins with a tiny grain of dust or salt, a seed around which water vapor condenses and freezes. Because of the natural angle between the atoms in a water molecule, the ice crystal grows outward in 6 directions, creating a perfectly symmetrical hexagon. As the crystal drifts through the sky, Changing humidity and temperature sculpt its arms into delicate patterns. Some become long and needle-like, others wide and feathery. The air currents shape each one differently, yet all obey the same molecular geometry. The result is a crystalline masterpiece that embodies both order and chance. No designer could reproduce the infinite variety of these tiny frozen mandalas. Each flake that lands on your sleeve is a work of molecular art, crafted by air, time, and temperature, a silent record of the sky's chemistry written in the language of ice. No two snowflakes are truly identical at the molecular level. Every snowflake follows the same geometric rules, yet the path each one takes through the clouds ensures that no two can ever be exactly alike. As they drift downward, snowflakes move through layers of air with slightly different humidity and temperature. Each subtle shift alters how fast water vapor freezes onto its surface, changing the pattern of branches and ridges. Even if two snowflakes started with the same shape, their journeys through the atmosphere would make them diverge into unique forms. Under a microscope, their differences are endless, from the thickness of each arm to the minute angles between crystal planes. The result is a natural infinity of design emerging from one simple molecule. Every snowfall is both repetition and originality at once, a dance of symmetry and chance that never creates the same beauty twice. Water molecules constantly switch partners in trillionths of a second. In liquid water, the molecules are never still. They bond together through hydrogen attractions, but these bonds last for only the briefest moments. Within a trillionth of a second, they break apart and reform elsewhere, causing each molecule to exchange partners continuously. This restless dance gives water many of its strange properties, from its ability to store heat to its smooth flow. If you could watch at the atomic scale, the calm surface of a lake would appear as a storm of motion, a whirl of collisions and connections forming and dissolving faster than thought. Each molecule is pulled between order and chaos, creating a liquid that is both cohesive and flexible. In every droplet, an invisible choreography unfolds, endless and tireless, a reminder that what appears still is, in truth, always alive with motion. Each molecule spins and vibrates in endless motion. Even when water appears still, its molecules are alive with energy. They rotate, twist, and vibrate in a rhythm dictated by temperature and the subtle tug of quantum mechanics. Every vibration stretches the tiny bonds between hydrogen and oxygen, then releases them like a pucked string. These oscillations occur trillions of times each second, turning every drop into a miniature symphony of motion. Even at the coldest temperatures, the molecules never truly stop moving. They retain a faint hum of energy called zero-point motion, proof that absolute stillness is impossible. This constant activity allows water to absorb and distribute heat, to dissolve substances, and to maintain the delicate chemistry of life. Beneath the calm surface of a pond lies a hidden orchestra of vibrations, a microscopic rhythm that has played since the first oceans shimmered beneath a young and glowing sky. A single drop contains more molecules than stars in the universe. A single raindrop may seem ordinary, but within it lies a population beyond imagination. Roughly 10 sextillion molecules of water inhabit that tiny sphere, a number greater than all the stars that fill the observable universe. Each one is a perfectly balanced trio of atoms, held together by the most fundamental forces in nature. These molecules collide constantly, binding and breaking with microscopic precision, creating the flowing dance that defines liquid water. In that single drop, countless bonds form every moment, generating a motion so complex that it defies easy description. When sunlight strikes the surface, those same molecules refract and scatter light, creating rainbows and reflections. It is staggering to realize that something so small can contain so much structure. Every raindrop is a universe in miniature, full of motion, energy, and the intricate architecture of life's most essential substance. Water can tunnel through barriers of the quantum level. In the strange world of quantum mechanics, water does things that seem impossible in the larger world we know. Its hydrogen atoms can occasionally slip through barriers that should stop them completely, a phenomenon known as quantum tunneling. Instead of climbing over an energy wall, the particle simply appears on the other side, guided by probability rather than force. This subtle behavior affects how water interacts with biological molecules, influencing the structure of DNA and the function of enzymes inside living cells. In deep space, tunneling even helps water form in the coldest regions where chemical reactions should be impossible. It is as though the molecule remembers paths beyond classical limits, moving through matter in ways that defy logic. Within each droplet lies this quiet magic, a reminder that reality itself is less solid and more mysterious than it appears to be. It is one of the few molecules that defies simple chemistry. For all its familiarity, water behaves unlike almost any other known substance. It should boil at temperatures far below those we experience, and it should sink when frozen, yet it does neither. Its heat capacity is higher than expected, allowing it to absorb vast amounts of energy without rapid temperature change. Scientists once assumed its properties could be predicted from simple molecular models, but water resists such simplicity. Its hydrogen bonds shift and reorganize in ways that make it act both ordered and chaotic at once. This strange behavior stabilizes climates, protects living organisms, and sculpts entire ecosystems. Without these quirks, Earth would be unrecognizable. Oceans would behave differently, weather would change, and life might never have arisen. What appears simple in a glass is actually one of the most complex and beautifully balanced substances in all of nature. Liquid water can exist in two distinct structures at once. Recent discoveries suggest that water is not a single, uniform liquid, but a constantly shifting mixture of two distinct molecular arrangements. One form is dense and tightly packed, while the other is open and loosely bonded. These structures alternate within the same droplet, fluctuating over tiny scales of time and space. The balance between them depends on temperature and pressure, and it may help explain water's peculiar behavior when cooled near freezing. This dual personality means that even within one glass of water, there are regions that act almost like two separate liquids coexisting in harmony. Such complexity challenges our understanding of matter itself. It shows that even something as ordinary as a puddle contains hidden worlds of molecular motion, a living landscape where order and disorder mingle in perpetual equilibrium. Scientists believe water may have multiple liquid phases. As researchers study water under extreme conditions, they have begun to uncover evidence that it can exist in several different liquid forms depending on temperature and pressure. These phases are not simple changes in density, but entirely distinct arrangements of molecules, each with its own internal structure. At supercooled temperatures, water seems to divide into a lighter, open network and a denser, more compact one, switching between them in fractions of a second. This discovery could explain many of water's long-standing mysteries, from its heat capacity to its unusual freezing behavior. It suggests that what we think of as a single substance may actually be a family of liquids, layered within one another like invisible worlds. Even after centuries of study, water continues to reveal deeper layers of complexity, reminding us that simplicity often hides the most profound secrets of all. Water has the highest surface tension of any common liquid. Water's surface is more than a boundary between liquid and air. It is a flexible film held together by invisible forces. Each molecule at the surface clings tightly to those beside and beneath it, creating an elastic tension stronger than in almost any other liquid. This property allows water droplets to form perfect spheres in space and enables insects and dust to rest delicately on its surface. It also helps water climb upward through plant stems and form beads that roll across leaves after rain. Without this tension, dew would not sparkle, bubbles would not hold their shape, and the delicate architecture of raindrops would collapse. What we see as a smooth surface is, at a molecular level, a network of tiny attractions strong enough to bind worlds together in softness. Tiny insects can walk on water thanks to that tension. To small creatures like water striders, the surface of a pond behaves almost like solid ground. Water's surface tension forms a flexible skin strong enough to support their weight, provided they distribute it carefully. Their long, slender legs are covered in fine hairs that repel water and trap tiny pockets of air, preventing them from breaking through. With each movement, they press gently against the surface, creating dimples that push back and propel them forward. The physics is delicate yet perfectly balanced, allowing these insects to glide with effortless grace. They can turn, jump, and even skate across moving currents without sinking. Each ripple they create sends signals through the water, revealing nearby movement or prey. In their small world, gravity and surface tension exist in perfect partnership, demonstrating how even the smallest life can master the laws of nature. Some spiders build underwater air bubbles to breathe. The diving bell spider is one of nature's strangest engineers. It lives almost entirely underwater but breathes air. To do this, it spins a web between the stems of plants below the surface and traps a shimmering bubble of air within it. The spider carries air from above, clinging to the bubbles on the fine hairs of its abdomen, and releases them into the silk dome until it grows large enough to live inside. The structure works like a natural lung, allowing oxygen from the surrounding water to diffuse in while carbon dioxide seeps out. This means the spider rarely needs to surface. Within that tiny underwater chamber, it hunts, feeds, and raises its young. It is a delicate balance of physics and biology, a small living example of how life can invent extraordinary ways to coexist with water's quiet rules. Water striders skate using invisible dimples on the surface. Water striders seem to glide effortlessly across ponds, moving with precision and silence. Each step creates a small depression in the water's surface, a dimple that pushes back and propels the insect forward. The legs are covered with microscopic hairs that trap air, keeping them dry and buoyant. By adjusting how they press against the water, the striders generate thrust without ever breaking the surface. Their movements are so controlled that they can leap from water into air, balancing two worlds with the same elegance. This ability is a masterpiece of adaptation, showing how evolution can turn the physics of tension into a mode of transportation. Watching them skate across still water is like witnessing gravity briefly lose its grip, a dance of balance and buoyancy perfected over millions of years. Water is a near-universal solvent that dissolves almost everything. Water's ability to dissolve substances is unmatched. Each molecule has a positive and a negative side, giving it polarity. When it encounters a solid, those opposing charges surround the particles and gently pull them apart. This process allows minerals, salts, and countless compounds to disperse evenly through the liquid. Without it, there would be no nutrient flow in soil, no oxygen exchange in blood, and no chemistry of life inside cells. Water's dissolving power also shapes landscapes, breaking down rock, carrying minerals to the sea, and building new formations over time. Every droplet is both a sculptor and a messenger, transferring matter from one place to another. In its patient way, water blurs the boundary between substance and motion, revealing that even the hardest materials eventually yield to the gentlest force of all. It can even carve stone over geological time. Water is soft enough to touch and strong enough to shape worlds. Over millennia, rivers and rain carve through mountains, dissolving minerals and carrying them away grain by grain. When water seeps into cracks and freezes, it expands, breaking rock apart with quiet persistence. These tiny fractures grow into canyons and caves, sculpting the landscape with patience beyond comprehension. The Grand Canyon itself is a record of water's steady work, each layer of exposed rock a page in a story written by rivers. Even underground, streams etch labyrinths of limestone into vast caverns. The process is slow, silent, and unstoppable. It proves that true power does not always roar. Sometimes it flows gently, shaping stone with time instead of force, revealing that nature's greatest strength often lies in persistence and calm. Pure water is actually a poor conductor of electricity. Contrary to popular belief, pure water does not conduct electricity well. Its molecules are tightly bonded and contain no free charges to carry current. Only when salts, minerals, or other impurities dissolve into the liquid does it become a true conductor. In nature, water almost always contains these ions, which is why lightning, wires, and energy interact with it so dramatically. In laboratories, scientists can produce water so pure that it briefly insulates against electric flow, though it quickly absorbs contaminants from air and surfaces. This balance between purity and conductivity is part of what makes water such a fascinating medium. It can act as both pathway and barrier, depending on its contents. Each droplet is a vessel of potential, equally capable of transmitting energy or resisting it, depending on the invisible chemistry within. It becomes conductive only when ions are present. Electric current moves through water only when it contains ions, the charged particles that come from dissolved salts and minerals. When these ions drift between water molecules, they create channels through which electricity can travel. The more ions present, the stronger the current can flow. Seawater is an excellent conductor because it contains countless sodium and chloride ions, while distilled water, stripped of impurities, barely conducts at all. This simple principle governs many natural processes, from how marine life senses electrical fields to how storms interact with the ocean. Inside the human body, the same chemistry allows nerve signals to pass through water-rich tissue. Electricity in water is therefore not a mystery, but a dialogue between charge and motion, a quiet exchange of energy that underlies both life and the rhythms of the earth itself. Water has a memory of heat and movement. When water is heated or cooled, it changes not only in temperature but in structure. The hydrogen bonds connecting its molecules shift, forming and dissolving in new configurations that can persist briefly even after equilibrium returns. This gives water a subtle trace of its past, a faint echo of its motion, turbulence, and exposure to warmth or cold. The same sensitivity helps explain phenomena like supercooling, where liquid remains unfrozen below zero because its internal structure resists crystallization. Scientists have measured these temporary molecular patterns and found that water's arrangement can retain hints of its recent conditions before returning to a balanced state. It is an incredibly responsive substance, reacting to pressure, vibration, and light in ways few materials can match. Each ripple, each movement of heat or sound leaves a momentary signature within it. Every drop becomes a fleeting archive of the world that has just passed through. It stores energy as hydrogen bonds that constantly form and break. Within every drop, countless hydrogen bonds link one molecule to another. These faint attractions arise from the uneven distribution of electrical charge, connecting the slightly positive hydrogen of one molecule to the slightly negative oxygen of another. Each bond lasts only a trillionth of a second before shifting elsewhere, creating an ever-changing network that stores and releases energy in tiny pulses. When bonds form, they release warmth. When they break, they absorb it. This constant exchange allows water to regulate temperature, softening the extremes between heat and cold. Oceans hold vast reserves of energy because of this process, releasing it gradually to shape winds, currents, and climate. Inside living organisms, these same interactions stabilize cells and maintain balance. Water's energy storage is not mechanical but rhythmic, a microscopic dance of attraction and release that turns chaos into harmony, keeping the planet and every creature on it alive. The shape of water molecules determines how it behaves. A molecule of water may appear simple, yet its structure defines nearly everything about the world we know. The oxygen atom holds electrons more tightly than the two hydrogen atoms attached to it, creating a separation of charge across the molecule. Instead of forming a straight line, the atoms connect at an angle, giving the molecule a slight asymmetry. This bent geometry makes one side faintly negative and the other faintly positive, turning each molecule into a tiny magnet. Because of this, water molecules attract one another and form the hydrogen bonds that make the liquid cohesive. From that geometry arise its most extraordinary traits: the ability of ice to float, the surface tension that shapes raindrops, and the power to dissolve countless substances. If the molecular angle were even slightly different, the chemistry of life could not exist. Within that small shape lies perfection born of balance. Those molecules have a bent geometry that creates polarity. Each molecule of water carries an internal tension between its parts. The oxygen atom pulls electrons closer, while the two hydrogens give up a little of their own. This unequal sharing of charge produces a subtle electrical imbalance called polarity. It makes one side of the molecule slightly negative and the other side slightly positive, causing nearby molecules to align and attract each other. This attraction forms a vast network that links every molecule in a shifting web of bonds. Polarity allows water to cling to surfaces, to dissolve minerals, and to act as a bridge between many different substances. It gives droplets their rounded shape and lets waves flow without separation. In every ocean and cloud, this gentle electrical structure is what holds the world together. Proof that even the quietest forces can shape entire planets. That polarity lets water stick to itself and to you. Water's ability to adhere and cohere comes from the small electrical charges within its molecules. Each one acts like a magnet, clinging to others nearby while also bonding to different materials. This dual power of adhesion and cohesion lets raindrops form, rivers climb through soil, and sweat cling to skin. It is what makes the surface of a puddle ripple when touched and allows a tear to roll smoothly down a cheek. In your own body, this same property helps water travel through veins and tissues, carrying nutrients where they are needed most. The way it holds together gives it strength and softness at once. It connects everything it touches, linking living and non-living worlds through attraction at the smallest scale. Every drop is a meeting point between molecules, each one reaching out, pulling in, and holding life close. Water's polarity makes life's chemistry possible. Life depends on molecules that can dissolve, mix, and react, and water provides the perfect environment for that to happen. Its polarity allows it to separate charged particles, breaking them apart so that reactions can occur freely. Inside cells, it surrounds complex molecules like proteins and DNA, keeping them stable while allowing them to move and change shape. Nutrients, minerals, and gases travel through it effortlessly, drawn by the same gentle electrical forces that bind the molecules together. Without this property, biological chemistry would grind to a halt. Cells would become rigid, and reactions would stop. Water's polarity turns it into a universal medium for transformation, a living bridge that allows matter to rearrange itself. It is not simply a background substance, but an active participant in creation, the invisible stage upon which all living chemistry performs its endless dance of renewal. Your body is mostly water, but it is not evenly distributed. The human body is made mostly of water, yet it is not spread equally throughout. Muscles, blood, and the brain contain far more than bones or fat. Inside cells, water forms the majority of the environment where chemical reactions occur, while outside, it helps transport nutrients and remove waste. Even within a single organ, different layers hold different concentrations depending on their function. This uneven distribution allows the body to remain flexible, balancing hydration where it is needed most. The heart depends on fluid pressure to pump efficiently. The eyes rely on it for clarity, and the skin uses it to regulate temperature. Every heartbeat, breath, and movement depends on precise management of water across tissues. The body's design is a masterpiece of distribution, a flowing equilibrium that keeps life moving quietly from one moment to the next. Your brain is mostly water, and it conducts tiny electric currents. The human brain is composed primarily of water, and that fluidity is what allows thought itself to occur. Electrical impulses travel through networks of neurons, each signal relying on ions that drift through water-filled channels. Without that fluid medium, the brain's delicate chemistry could not function. The balance of water inside and outside each neuron determines how easily these currents move, shaping perception, memory, and mood. Even slight dehydration can alter brain performance, slowing thought and blurring focus. Yet water does more than conduct electricity. It cushions the brain within the skull, absorbs shocks, and helps regulate temperature. Every flicker of consciousness, every idea and dream depends on the quiet presence of this liquid. The mind is not just housed in water but sustained by it, a sea of thought carried within a living tide. Blood is a suspension of cells flowing in water. What we call blood is a complex river of life. Its liquid portion, plasma, is mostly water, carrying red and white cells, platelets, nutrients, and waste in constant motion. The fluid's ability to dissolve salts, sugars, and gases allows it to transport oxygen from the lungs to tissues and carbon dioxide back again. Water keeps this mixture thin enough to flow, yet thick enough to carry what the body needs. Without it, circulation would halt, and cells would starve of energy. The same properties that, like rivers carve through land, allow blood to move smoothly through arteries and veins. Every heartbeat sends water through a network that nourishes billions of living cells. Within each pulse, chemistry and physics work in harmony, proving that life is not a static thing but a continual flow shaped by liquid balance. DNA floats perfectly in a watery world. The double helix of DNA, the molecule that carries the instructions for life, exists in an environment that could not be more suited to it. Water surrounds the helix, stabilizing its shape while still allowing it to twist, unwind, and copy itself. The molecule's outer edges attract water, while its inner bases hide from it, creating a natural boundary that preserves its structure. This relationship is so precise that DNA could not function properly in any other liquid. Water's ability to dissolve and rearrange molecules makes replication possible, guiding the endless copying that sustains every living organism. Each cell is a droplet of this chemistry, where water acts as both solvent and protector. It cradles the code of life gently, allowing the past to be written into the future with every replication of its spiraling script. Proteins fold correctly only in water. Proteins are long chains of amino acids that must fold into specific shapes to function. In the absence of water, they collapse incorrectly or fall apart. The reason lies in the delicate push and pull between water-loving and water-avoiding regions along each chain. Water guides these sections into their proper places, allowing the protein to take on its final form. Once folded, the same fluid stabilizes it, surrounding it like an invisible guardian. Without this environment, life's machinery would fail. Enzymes could not catalyze reactions, muscles could not contract, and cells would lose their structure. Each fold is a dialogue between matter and moisture, a quiet negotiation where the liquid determines the outcome. The simplicity of water hides its genius. It is both participant and architect in the construction of every living form. Cells keep their shape because of water pressure. Every living cell is like a small balloon filled with fluid. The pressure created by water inside gives it structure and stability, allowing it to maintain its form even when surrounded by changing environments. In plants, this internal pressure, called turgor, keeps stems upright and leaves expanded. In animals, it supports the membranes that define each cell's boundary. Without it, cells would collapse or shrivel. This inner force also allows materials to move in and out, driving the flow of nutrients, gases, and signals. The same gentle push that shapes a leaf's curve or a vein's pulse is the quiet strength that keeps life intact. In every living thing, water acts as both scaffolding and support, its pressure maintaining form while still allowing the freedom of movement that defines vitality. Water acts like a cushion for the brain and spine. The brain and spinal cord float in a clear fluid made mostly of water. This liquid, called cerebrospinal fluid, absorbs shock, cushions impacts, and provides a stable environment for delicate tissues. Every movement of the head or body sends gentle waves through this protective sea, preventing injury and maintaining chemical balance. The same water also delivers nutrients and removes waste, circulating continuously through hidden channels. Without it, even minor impacts could cause severe damage, and the nervous system could not regulate itself. The presence of this fluid is a reminder that even our most advanced organs rely on simple physical principles for safety. It is water's ability to absorb force and distribute pressure that keeps the mind safe within its fragile shell, a silent guardian surrounding thought and memory. Tears and saliva are complex mixtures of water and chemistry. Although they seem simple, both tears and saliva are intricate solutions where water plays the leading role. In tears, it dissolves salts and proteins that protect and heal the eyes, washing away dust and maintaining moisture. In saliva, it blends with enzymes that begin digestion, softening food and helping speech. The water content allows these fluids to spread easily across delicate tissues, creating thin, uniform films that prevent dryness. They also carry subtle signals of emotion and health, changing slightly with stress, fatigue, or joy. Every droplet is a blend of biology and feeling, reflecting both physical need and the quiet emotional chemistry of being alive. The next time you swallow or blink, you participate in a process that connects sensation, survival, and water's endless adaptability. Water carries heat through the human body better than air. Water has an extraordinary ability to hold and transfer heat. Inside the body, this makes it the perfect medium for maintaining temperature. Blood, sweat, and internal fluids all rely on this property to move warmth where it is needed. Because water conducts heat far more efficiently than air, it allows the body to regulate temperature smoothly, preventing dangerous fluctuations. When you exercise, the heat generated by muscles is absorbed by water-rich tissues and carried away, protecting vital organs. The same principle applies to the planet, where oceans distribute energy across the globe. Whether within a cell or an ocean current, water's thermal stability forms the foundation of balance. It is nature's quiet method of harmony, carrying warmth through life with precision and grace. Sweat uses evaporation to cool the body. When the body overheats, it releases moisture through glands in the skin. As the sweat evaporates, it draws energy away in the form of heat, cooling the surface. This simple process relies on the high heat capacity of water, which requires significant energy to change from liquid to vapor. The same principle is used by plants that release moisture through their leaves, cooling themselves as water turns to mist. In both cases, evaporation provides a natural form of temperature control, powered entirely by physics. Each droplet that leaves the skin carries away warmth, transforming discomfort into relief. It is a process so ordinary that we rarely notice it, yet without it, life in hot environments would be impossible. Through evaporation, water turns the invisible energy of the sun into comfort and survival. Humans can survive weeks without food, but only days without water. The human body depends on water for nearly every function. It carries nutrients, removes waste, regulates temperature, and allows countless chemical reactions to occur within cells. While fat and muscle can provide stored energy for weeks, there is no reserve for hydration. Every breath, every drop of sweat, and every exhale releases moisture. When that loss exceeds replacement, organs begin to fail. Dehydration thickens the blood, strains the heart, and disrupts the delicate chemistry of the brain. Within days, the lack of water becomes fatal. It is a humbling reminder that life exists only as long as balance does. Even surrounded by abundance, survival depends on a single clear liquid that makes up most of who we are. Every breath you exhale contains water vapor. With each breath, the body releases moisture into the air. The lungs are lined with thin films of water that help exchange gases, and as air passes through them, it becomes saturated with vapor. On a cold day, you can see this invisible process as mist escaping into the atmosphere. In a single day, an average person exhales several hundred milliliters of water, enough to fill a small cup. This continuous cycle connects each living being to the planet's atmosphere, contributing to humidity and weather patterns. Every sigh and whisper releases part of the body's internal ocean back into the sky. In this small but constant exchange, we become part of Earth's water cycle, breathing with the same rhythm as rain, wind, and cloud. Your body loses water even while you sleep. During rest, the body continues to release moisture through breathing, skin, and natural processes. Overnight, the air you exhale carries vapor from your lungs, and the warmth of your body allows it to evaporate from the skin. By morning, several hundred milliliters of water may have been lost without notice. This is why hydration is essential after waking. The process is gentle and unending, part of the same rhythm that governs tides, rainfall, and life itself. Even in stillness, the exchange continues, as if the body dreams in water. Every night is a reminder that existence is never separate from flow. The average cloud weighs hundreds of tons of water. Though clouds appear weightless, they are made of billions of tiny droplets suspended in air. A single fluffy cumulus cloud can hold hundreds of tons of liquid water spread across a vast volume. The droplets are so small that rising warm air supports them, keeping them aloft. Eventually, when they merge and grow, gravity wins, and rain begins to fall. Each cloud drifting across the sky is a floating ocean, moving silently with the wind. The scale is so enormous that every one of them carries the potential for rivers, storms, and renewal. To look up is to see water in its most ethereal form, hovering between sky and earth, waiting for the moment when gravity calls it home. Yet it floats because its droplets are so small. a cloud seems soft and weightless, drifting gently across the sky. In truth, it is a vast collection of tiny droplets, each one made of liquid water. A single cloud can contain hundreds of tons of water, yet it floats because the droplets are so small that gravity has little effect on them. Rising warm air supports them, creating an invisible balance between upward lift and downward pull. Each droplet is less than the width of a human hair, light enough to be carried for miles. They collide, merge, and separate again, moving in endless motion. When enough of them join together, they become too heavy to remain aloft and fall as rain. The floating of clouds is a perfect example of nature's equilibrium, where air and water dance together, suspended between sky and earth, creating beauty from balance and stillness from constant movement. Water vapor is the most abundant greenhouse gas. Among all the gases that warm our planet, the most powerful and plentiful is water vapor. It forms naturally through evaporation from oceans, lakes, and living organisms. This vapor traps heat radiating from Earth's surface, holding it in the lower atmosphere and keeping the planet warm enough for life. Without it, the world would be a frozen desert. Yet it does not merely trap heat, it regulates it. Clouds form when vapor condenses, reflecting sunlight back into space and cooling the planet. In this way, it acts as both blanket and mirror. The balance between these two effects determines weather patterns and climate stability. Every droplet that evaporates becomes part of this vast thermal cycle, rising invisibly before returning as rain. Water vapor is not only a gas but a guardian, maintaining the gentle warmth that allows oceans to flow and forests to grow beneath the sky. It traps heat, but also helps regulate planetary temperature. The ability of water vapor to absorb and release heat makes it the planet's most subtle climate control system. As sunlight warms oceans, lakes, and soil, water turns to vapor and rises into the air. There, it absorbs heat, preventing the surface from overheating. When it condenses into clouds, it releases that energy back into the atmosphere, fueling winds and storms that redistribute warmth across the globe. This constant cycle keeps the world's temperature in delicate balance. Without it, the tropics would become unbearably hot, and the poles would freeze beyond life's reach. Even small changes in the amount of vapor can shift weather and seasons. Every gust of wind and every drifting cloud participates in this ancient exchange, a breathing rhythm of evaporation and condensation that keeps the Earth temperate, alive, and in motion through endless cycles of heat and calm. Earth's oceans hold 97% of its water. Nearly all of Earth's water rests in the vast embrace of the oceans. They cover more than 2/3 of the planet's surface and contain 97% of its total volume. The remaining fraction exists as ice, rivers, lakes, underground aquifers, and in the atmosphere. The oceans are the great regulators of life and climate. They absorb heat from the sun and move it around the world through immense currents, shaping winds, storms, and rainfall. Within their depths, live creatures that generate oxygen and form the base of the global food web. They reflect the sky, sculpt the coasts, and hold the memory of continents that have risen and fallen through time. To stand at the edge of the sea is to face the source of nearly everything alive. Each wave carries not only salt and motion, but also the long story of the planet's enduring pulse. Only a tiny fraction exists as fresh water. Of all the water on Earth, only a small portion is fresh and available for drinking. Less than 3% is free of salt, and most of that is locked away in glaciers and polar ice caps. The remaining portion flows through rivers, lakes, and underground reserves, forming the lifeblood of all land ecosystems. Every drop that flows from a mountain spring or falls as rain carries the weight of scarcity. It supports forests, fills reservoirs, and sustains billions of living things. The cycle that renews it is ancient, driven by sunlight and gravity, yet fragile under imbalance. The journey from cloud to stream to sea repeats endlessly, but the usable portion remains a precious minority. To drink a glass of fresh water is to experience one of the rarest materials on the planet, a gift sustained by the constant breath of the sky and the patience of the earth. Most fresh water is locked away in ice or underground. The majority of Earth's fresh water does not flow on the surface but hides beneath it or within frozen realms. Glaciers and polar ice caps contain enormous reserves, holding centuries of snowfall compressed into crystal layers. Underground aquifers store even more, trapped in rock and soil since ancient times. These unseen reservoirs shape human history, feeding wells, springs, and rivers. In some places, they are renewed each year by rainfall. In others, they have been sealed away since the last ice age. The frozen and buried waters act as planetary savings accounts, releasing their contents slowly to maintain balance in the hydrological cycle. If all the ice melted at once, sea levels would rise dramatically, reshaping continents. Yet even hidden and still, this stored water continues to influence weather, tides, and temperature, quietly linking the frozen poles with the living heart of the Earth. The deepest liquid water lies miles beneath Earth's crust. Far below the surface, beneath layers of rock and pressure, liquid water still exists. It moves through pores and cracks in the crust, heated by the planet's inner warmth. Some of these subterranean reservoirs lie miles deep, held within mineral structures that trap them under immense weight. This ancient water may have been sealed there since Earth's earliest days, untouched by sunlight or air. Scientists have found microbial life thriving in such environments, surviving in complete darkness on chemical energy alone. These deep aquifers remind us that water is not confined to oceans and rivers. It seeps into every corner of the planet, filling fractures, caverns, and crystal lattices with its quiet persistence. The hidden lakes and flows far below our feet are as much a part of the global water system as the seas above, proof that life's foundation runs deeper than we can see. Liquid lakes exist beneath Antarctic ice sheets. Beneath the miles-thick ice of Antarctica lie hidden lakes of liquid water. They remain unfrozen not because of heat from above, but because of pressure from the ice and warmth from the earth below. Some of these lakes have been sealed off for millions of years, isolated from the surface since before humans existed. They form unique ecosystems where microbes survive in cold darkness without sunlight. Lake Vostok, one of the largest, stretches for hundreds of miles under the ice, its surface untouched by air or wind. Each of these subglacial lakes is a time capsule, preserving clues about ancient climates and the boundaries of life. Scientists study them to understand how organisms might exist on other frozen worlds, where ice hides oceans below. In these secret lakes, the planet holds memories of a colder, older Earth, still alive beneath its frozen shield. There may be hidden oceans beneath other worlds' ice shells. In the outer solar system, far from the warmth of the sun, several moons conceal oceans beneath frozen crusts. These hidden seas are kept liquid by internal heat and the pull of gravity from their parent planets. Beneath layers of ice miles thick, they may hold more water than all of Earth's oceans combined. Scientists believe these secret worlds, though shrouded in darkness, could provide the right conditions for life. Chemical energy, not sunlight, might sustain ecosystems there just as it does around deep-sea vents on Earth. The discovery of such oceans has transformed our view of habitability. Water, once thought to be rare beyond Earth, now appears abundant across the cosmos. Each icy moon whispers of unseen depths, reminding us that life's potential may not depend on light at all, but on the quiet persistence of liquid water in the dark. Jupiter's moon, Europa, may hold twice as much water as Earth. Beneath its gleaming crust of ice, Europa hides an immense global ocean. Despite being smaller than our moon, it may contain twice the volume of water found on Earth. Tidal forces from Jupiter's gravity stretch and squeeze the moon, generating heat that keeps its ocean liquid. Cracks and ridges on its surface mark where this subsurface sea may reach upward, freezing and breaking through. Beneath the ice, chemical reactions between rock and water could provide the energy needed for life. No sunlight reaches those depths, yet entire ecosystems might exist, nourished by minerals and heat alone. Scientists dream of one day sending probes to drill through the ice and taste its waters, to discover whether Europa's silent ocean breathes with life. The possibility that another world hides a living sea beneath frozen light continues to stir wonder in all who gaze toward Jupiter's moons. Saturn's moon Enceladus shoots water geysers into space. At the edge of Saturn's rings orbits a small, bright moon that releases fountains of water from its frozen surface. Beneath Enceladus's crust lies a global ocean kept warm by tidal forces that flex and squeeze its interior. Cracks near the South Pole act like vents, spraying plumes of vapor and ice into space that rise for hundreds of kilometers before drifting back down like gentle snow. These geysers contain salts and organic molecules, suggesting that chemical reactions occur in the dark sea below. Some of the escaping water becomes part of Saturn's outermost ring, spreading the moon's breath across the planet's vast system. To watch those jets is to see an entire world exhaling, a frozen sphere that still hides warmth and movement within. Enceladus has become one of the most promising places beyond Earth to search for life, a distant ocean calling across the void. Water has been found in the atmospheres of distant exoplanets. Astronomers studying stars far beyond our solar system have detected traces of water vapor surrounding distant planets. Using space telescopes that analyze starlight as it passes through planetary atmospheres, they can identify the spectral signature of water, a faint pattern of absorption that reveals its presence. These observations have found vapor on worlds that range from scorching gas giants to smaller planets orbiting cooler stars. In some cases, the amounts suggest the possibility of clouds, rain, and even oceans. The discovery changed how we think about the universe, showing that water is not unique to Earth, but common throughout the galaxy. Every detection expands the dream of finding another habitable world. The same molecules that fall as rain here may drift as mist on a planet hundreds of light years away, whispering the same quiet chemistry that once gave rise to life. Even interstellar clouds contain water vapor. Between the stars, in regions that appear dark and empty, immense clouds of gas and dust drift slowly through space. Within these nebulae, molecules form on the surfaces of icy grains, and among them is water. Though extremely diffuse, these clouds contain enough vapor to fill oceans if gathered together. When new stars ignite, the surrounding heat releases that frozen water into space, seeding the material that will later form planets and comets. Every world that holds liquid water may owe its origins to these interstellar nurseries. The presence of water so far from any star reminds us that the universe itself is a generator of life's ingredients. Even in the coldest darkness, chemistry continues. Each molecule becomes part of a vast cycle that stretches from the birth of stars to the formation of oceans, linking the most distant regions of space to the drops we drink on Earth. Comets carry ancient water across the solar system. Comets are frozen time capsules, relics from the birth of the solar system, that still carry the original water from its formation. Made of ice, rock, and dust, they travel on long elliptical paths that bring them close to the sun and then send them back into the deep cold. As they warm, the ice within them turns to vapor, forming glowing tails that stretch for millions of kilometers. Each pass through sunlight releases a little of their cargo into space, scattering water and organic molecules wherever they go. Some of this material may fall onto planets, enriching them with new ingredients. Many scientists believe that a portion of Earth's water arrived this way. Comets are both messengers and midwives, carrying the ancient chemistry of creation through space, reminding us that even in darkness, the seeds of oceans and life can drift silently between the stars. Earth's water may have come from colliding comets and asteroids. When Earth was young, its surface was molten and dry, constantly bombarded by debris from space. Over time, some of those impacts delivered icy material from comets and water-bearing minerals from asteroids. As the planet cooled, the vapor they released condensed into liquid, forming the first oceans. The evidence lies in isotopes, the chemical fingerprints that show similarities between Earth's water and that found in certain types of meteorites. The process may have taken millions of years, with countless collisions slowly transforming a barren world into a blue one. Each impact carried more than destruction, it carried renewal. The water that fills our seas and rivers may once have been locked inside drifting stones, waiting for gravity and time to bring it home. In that ancient reign of rock and ice, the stage for life itself was quietly being set beneath the newborn sun. Some meteorites still contain locked-in water minerals. Scattered across deserts and frozen plains, meteorites that fall to Earth often hold minerals that once trapped water deep within their crystal structures. These fragments come from asteroids that formed billions of years ago, long before our planet existed. When scientists break them open, they find evidence of hydrated minerals, proof that liquid water once flowed through those parent bodies. Each stone becomes a record of an ancient process that shaped the solar system. Some meteorites even contain microscopic pockets of water, preserved since the earliest era of planetary formation. Studying them reveals that water was present throughout space from the beginning, woven into the fabric of rock and dust. Every recovered fragment is a message from the past, a reminder that the element that sustains us was once scattered through countless worlds, waiting to gather into the oceans we now know. Water may have existed on Mars for billions of years. The red planet bears countless scars of flowing water. Dry riverbeds, deltas, and valleys carve its surface, suggesting that ancient rains once fell there. Minerals found by rovers show patterns that can form only in the presence of liquid water, and polar ice caps still hold vast reserves of frozen material. For perhaps hundreds of millions of years, Mars may have had lakes and shallow seas, with a thicker atmosphere to keep them from evaporating. Over time, the planet lost much of its air to space, and with it, most of its water. Yet traces remain underground, and as frost that forms and disappears with the seasons. The evidence paints a picture of a world that was once warmer, wetter, and perhaps alive. Each discovery on Mars invites us to imagine its distant past, when its deserts were still touched by waves. Martian polar caps are made of both ice and frozen carbon dioxide. At Mars's poles lie bright white caps that expand and contract with the changing seasons. They are made not only of water ice, but also of frozen carbon dioxide, the same gas that forms dry ice on Earth. During the Martian winter, carbon dioxide from the atmosphere freezes onto the surface, creating a thick layer that can reach several meters deep. In summer, sunlight returns and sublimates the frozen gas, turning it directly back into vapor and revealing the underlying water ice. This seasonal cycle drives winds and dust storms across the planet, influencing its climate and shaping the landscape. The rhythm of freezing and thawing is a kind of Martian heartbeat, a yearly exchange between atmosphere and ground. Beneath those shimmering caps lies the key to the planet's history, a frozen archive that preserves the story of its vanished oceans. Water shaped Mars's canyons long ago. The largest canyon on Mars, Valles Marineris, stretches for thousands of kilometers and plunges deeper than Earth's Grand Canyon. Its vast chasms were not formed by wind alone. Evidence suggests that ancient water once flowed through them, carving channels and depositing sediments. In some places, minerals appear that could only have formed in liquid water, hinting at streams and lakes that existed billions of years ago. Over time, volcanic activity and tectonic shifts deepened the valleys, but the earliest shaping came from erosion and flow. The dry gullies we see today are remnants of that distant era. To study them is to read the signature of vanished rivers, the handwriting of water on a planet that lost its warmth. Mars remembers its oceans in stone, and each canyon stands as a monument to a time when the red planet once shimmered blue. Venus once may have had oceans that boiled away. Venus, now a world of heat and clouds, may once have been far more Earth-like. Early in its history, it likely possessed oceans of liquid water, but as the sun grew brighter, its surface warmed. The increased heat caused more water to evaporate, and the vapor trapped even more energy in the atmosphere, creating a runaway greenhouse effect. Eventually, the oceans boiled away, and ultraviolet radiation from the sun broke apart the remaining water molecules, allowing hydrogen to escape into space. What remained was a thick atmosphere of carbon dioxide and sulfuric acid clouds. Venus became a warning written in orbit, showing what happens when balance is lost. Yet in its high clouds, traces of water vapor still linger, faint ghosts of the seas that once covered its face, whispering of a world that could have been a sister to our own. Water is constantly escaping from Earth's atmosphere into space. Our planet is slowly leaking its water into the void. High above the clouds, at the edge of space, ultraviolet sunlight splits water vapor into hydrogen and oxygen. The light hydrogen atoms are so small that some gain enough energy to slip past Earth's gravity and drift away forever. Each escaping atom is a tiny thread pulled from an ocean that has existed for billions of years. The loss is minuscule, yet over geological time, it adds up. Planets like Mars lost their water this way long ago. Earth's magnetic field and thick atmosphere protect most of its supply, but the process never stops. Every second, thousands of hydrogen atoms escape, carrying with them the faint memory of seas and storms below. Space quietly drinks from our oceans, one invisible sip at a time, a reminder that even the most abundant elements are not truly eternal. The oceans are slowly growing saltier over time. The saltiness of the sea is not fixed. It increases very gradually as rain, rivers, and streams dissolve minerals from rocks on land and carry them into the oceans. Once there, most of those salts stay behind when water evaporates to form clouds, leaving the sea slightly more concentrated each cycle. This process has been unfolding for hundreds of millions of years. Although the change is slow, it shapes the chemistry of marine life, the formation of shells, and even the movement of ocean currents. Some areas become fresher when ice melts or rainfall increases, while others grow saltier through evaporation and heat. The ocean is always balancing itself, never still. The salt we taste in a single drop of seawater is ancient, the residue of mountains and rivers that have long since vanished, dissolved into the ever-changing equilibrium of the world's deep blue heart. Every grain of salt in the sea began as a rock. The salt that gives the ocean its flavor was once locked in stone. Rainfall, slightly acidic from carbon dioxide in the air, seeps into rock and soil, dissolving tiny amounts of minerals such as sodium and chloride. Rivers carry those dissolved particles to the sea, where they accumulate over time. The ocean never truly gets rid of them, because evaporation removes only pure water vapor. What remains behind grows slowly more saline as eons pass. In this way, every crystal of sea salt tells a geological story, a record of rain meeting mountain and mountain surrendering to time. The taste of seawater is the memory of continents breaking down grain by grain. Each wave that crashes against the shore carries the ghost of Stowe, a reminder that the land and the sea are not opposites, but partners in an eternal conversation of erosion and renewal. Under pressure, water can dissolve even more than it should. At great depths, where pressure is immense and light cannot reach, water behaves differently. It can dissolve minerals and metals far beyond what would be possible at the surface. In the crushing darkness of the deep ocean or within cracks in Earth's crust, superheated water becomes a powerful solvent. It leaches elements from rock, creating strange chemical mixtures that vent upward through fissures. When the fluid cools, minerals precipitate out, forming shimmering deposits of metal and crystal on the seafloor. These natural reactions shape the chemistry of the oceans and influence entire ecosystems. The ability of water to change its dissolving power with pressure and temperature is part of what makes it so extraordinary. It becomes both sculptor and messenger, carrying the signature of the deep earth upward and returning to the surface bearing whispers of heat, stone, and hidden transformation. Deep sea vents release superheated water rich in minerals. On the ocean floor, along spreading ridges and volcanic boundaries, cracks open to release jets of water heated by magma below. Though the surrounding sea is near freezing, these vents expel fluid that can exceed hundreds of degrees in temperature, yet it remains liquid because of the immense pressure. As it gushes out, the water carries dissolved metals and sulfur compounds that quickly cool and solidify, building towering chimneys of black or white mineral deposits. Around these vents flourish ecosystems unlike any other, thriving without sunlight. Bacteria feed on the chemicals in the vent water, forming the base of a food web that supports worms, crabs, and fish. Each vent is a world unto itself, a glowing oasis in the dark. The water that escapes there is not lifeless heat, but a cradle of chemistry, bridging the fiery interior of the planet with the cold expanse above. Life may have begun around those hydrothermal vents. Many scientists believe the first living organisms emerged not on the surface, but in the deep sea near hydrothermal vents. There, mineral-rich water mixes with cold seawater, creating steep chemical gradients and an abundance of energy. The walls of vent chimneys provide natural structures that can trap molecules, allowing simple carbon compounds to combine into more complex forms. Within those microenvironments, life's earliest chemistry may have taken hold, driven by heat and mineral energy instead of sunlight. The discovery of entire ecosystems living without photosynthesis suggests that biology can arise wherever water and chemistry meet in the right balance. In these dark, pressurized realms, life could have begun as gentle reactions within stone pores, slowly learning to store and use energy. Every breath we take may trace its lineage back to those silent vents, where the planet itself first stirred and learned how to live. Water's density reaches its maximum just above freezing. Most substances grow denser as they cool, but water reaches its greatest density at a temperature just above the freezing point. This unique behavior means that as lakes and ponds chill, the coldest water rises instead of sinking. The slightly warmer, denser water settles at the bottom, allowing life to survive through winter beneath a thin layer of ice. This delicate property influences the movement of ocean currents and the stability of climates worldwide. Without it, cold seasons would trap life under solid ice, and the rhythm of aquatic ecosystems would collapse. The temperature at which this occurs is one of the most precise balances in nature, determined by the geometry of water molecules as they begin to form crystal structures. That subtle shift, just a few degrees wide, is enough to decide whether a lake remains alive or falls into silent, frozen stillness. That quirk keeps lakes from freezing solid in winter. When winter descends and the air grows bitterly cold, lakes begin to freeze at the surface. Yet beneath the ice, liquid water remains, protected by one of nature's most fortunate coincidences. Because water is densest slightly above freezing, the coldest layer stays on top, forming ice that insulates the depths below. Fish, plants, and countless microorganisms continue their slow, quiet existence under this sheltering lid. If the water behaved like other substances, the entire lake would freeze from bottom to top, extinguishing all life each winter. Instead, it rests in equilibrium, conserving heat while allowing gas exchange through cracks and holes in the ice. Each frozen surface hides an entire living world beneath, a realm of muted colors and slow heartbeats waiting for spring. The quirk of density that protects them is a quiet miracle, a subtle triumph of geometry that keeps the planet breathing through the cold. Lakes turn over each year, mixing nutrients through water layers. In temperate climates, lakes experience a yearly rhythm known as turnover. During summer, warm water floats above cooler, denser layers below, creating a stable separation. As autumn chills the surface, the layers mix, circulating oxygen and nutrients from top to bottom. In spring, the process repeats when ice melts and winds stir the water again. This cycle nourishes aquatic life, preventing stagnation and distributing food and oxygen evenly. Without it, deep waters would become depleted, unable to support complex ecosystems. Turnover transforms still lakes into living systems that breathe with the seasons. It connects surface winds with underwater currents, birds in the air with fish in the depths. Each rotation of the planet brings this hidden stirring, a quiet renewal that has unfolded for thousands of years. Even in calm reflection, a lake is never truly still. It is always remembering how to move. Waves move energy, not water, across the sea. When we watch waves rolling toward the shore, it appears as though water itself travels great distances. In truth, it is energy that moves forward, while the water mostly circles in place. Each molecule follows an orbital path, rising and falling as the wave passes. The motion transfers energy from winds and distant storms across entire oceans, carrying it until it breaks upon the sand. This elegant mechanism allows weather, tides, and even earthquakes to send signals through the sea. The shape and rhythm of waves tell stories of distant winds, invisible storms, and the turning of the planet. Their ceaseless motion connects continents and climates, sculpting coasts and guiding migration. To watch a wave is to witness pure transfer, a pulse of energy rippling through water, echoing the heartbeat of the world itself, steady, patient, and eternal. Some waves travel the entire ocean without breaking. Far out at sea, waves can journey for thousands of miles before ever touching a shore. These are called swells, great rolling movements of energy set in motion by distant storms. Once created, they travel freely, guided by wind and gravity, crossing entire ocean basins in perfect rhythm. Their shapes remain smooth and regular, carrying the memory of the storm that gave them life. Ships at sea can feel their slow rise and fall long before land appears. When they finally meet shallow water, the lower part of the wave slows, while the top continues forward, rising higher until it curls and breaks. Yet for most of their voyage, they do not break at all. They are the long breath of the planet, silent messengers of weather systems half a world away, traveling endlessly until they release their stored energy on distant shores. Tides are the daily pulse of Earth's water. Every coastline feels the pull of the moon and, to a lesser extent, the sun. Their combined gravity draws the oceans into bulges that move around the world each day. The result is the rhythmic rise and fall of the tides, a planetary heartbeat that shapes coastlines, guides marine life, and has influenced human civilization for thousands of years. Tides fill and empty estuaries, carry nutrients into shallows, and create vast mudflats that feed entire ecosystems. They also drive currents that mix the oceans, redistributing energy and life. For creatures that live between land and sea, this rhythm is everything. It governs feeding, breeding, and migration. To stand on a beach at the edge of low tide is to witness the slow breathing of the earth itself, the perpetual motion of water pulled by celestial hands that never rest and never lose their strength. The moon's gravity pulls ocean bulges around the world. The gravitational attraction between Earth and the moon stretches the oceans into two vast bulges, one facing the moon and another on the opposite side. As the planet rotates, different regions pass through these high water zones, creating two tides each day. The moon's pull is strong enough to move entire seas, yet gentle enough that the motion feels almost like a whisper. The sun adds its influence, either amplifying the effect during full and new moons or softening it during quarters. This celestial interplay shapes the daily rhythm of the coasts and the lives of the creatures that depend on them. The tug of the moon also slows Earth's rotation slightly over time, gradually lengthening our days. Every tide is a trace of that bond, the silent evidence that our oceans dance in step with a companion world that glows above them in the night. There are tiny tides in the crust and atmosphere too. The pull of gravity that moves the oceans also stretches the solid Earth itself. Rocks rise and fall by small amounts each day, creating subtle land tides that can shift the ground by several centimeters. Even the atmosphere responds, forming slight bulges of air pressure that travel around the globe in time with the moon's orbit. These changes are invisible to the eye, but measurable by sensitive instruments. Though small, they affect the timing of earthquakes, the behavior of volcanic systems, and even the accuracy of satellite measurements. The entire planet moves gently to the same cosmic rhythm, as if breathing in unison with the sea. What we see as waves and tides on the surface are only part of a deeper pulse, a gravitational music that plays through air, water, and stone, uniting every layer of the Earth in quiet, celestial harmony. Water cycles through the air, land, and sea continuously. Every molecule of water is part of an endless journey that connects clouds, rivers, oceans, and living beings. Sunlight lifts vapor from the sea, forming clouds that drift across the sky. When they cool, the vapor condenses and falls as rain, feeding rivers and lakes, seeping into soil, and returning once more to the ocean. The same molecules can move through plants, animals, and even the air we breathe, before rising again as mist. This cycle has been operating for billions of years, maintaining balance between land and sea. It is so vast that the water in your glass today may once have fallen on a mountain, frozen in a glacier, or flowed through the roots of an ancient forest. The hydrological cycle is Earth's eternal heartbeat, the invisible thread that ties every living thing to the motion of the sky above and the depths below. The same molecules that once formed rain now flow in you. The water that runs through your body has existed since the beginning of the world. It once drifted through clouds, froze in ice, and cascaded down waterfalls long before you were born. Within your veins, ancient hydrogen and oxygen atoms are reunited, continuing their endless circulation through time. The molecules that now sustain your life may once have passed through the leaves of prehistoric trees or fallen as rain upon the backs of dinosaurs. When you exhale or sweat, they return to the air, ready to become part of the cycle again. There is no new water, only transformation. Each breath and heartbeat carries the same essence that has moved through oceans and skies for billions of years. You are part of the planet's great flow, a living vessel through which the story of water continues, calm and constant, from age to age. A single raindrop can take thousands of years to return to the sea. When rain falls, not every drop reaches the ocean quickly. Some sink deep into the ground, joining aquifers that flow slowly beneath the surface. Others freeze into glaciers, trapped for millennia before melting again. A drop may linger in a lake for decades, evaporate into clouds, or pass through living organisms on its way back to the sea. The journey of water is never straightforward. It wanders, resting in forests, rivers, and stones. Scientists studying isotopes and groundwater have traced some molecules that began their descent during the last ice age and are only now emerging in springs. Every raindrop is a traveler through time, following its own winding path. When it finally reaches the ocean, it rejoins the vast collective flow, completing a cycle that has no true beginning or end, only pauses in an eternal motion that connects all living worlds. Some water molecules spend centuries locked in ice. At the poles and on high mountains, layers of snow compress into ice that traps air, dust, and water molecules for hundreds or even thousands of years. These frozen archives preserve detailed records of past climates, storing the memory of ancient storms, volcanic eruptions, and atmospheric changes. Scientists extract ice cores to study those records, reading the layers like pages of a history book. Some of the water sealed within has not melted since long before human civilization began. When sunlight finally touches it again, the molecules are released to continue their journey through the atmosphere and sea. The frozen stillness of glaciers hides a slow rhythm, a patient heartbeat that moves only when the world grows warmer. Each melting drop is a messenger from the past, whispering of ages when the earth was younger, colder, and full of waiting light. Water transports nutrients through forests and rivers alike. In every ecosystem, water acts as a carrier, moving nutrients from one place to another. Rain seeps through soil, dissolving minerals that feed roots and trees. Rivers gather organic matter from decaying leaves and transport it downstream, where it nourishes fish and plants. Even in deserts, occasional rains trigger bursts of life as seeds awaken and microorganisms flourish. The movement of water connects all environments, turning local cycles into global systems. Every living thing depends on its ability to flow and transport. Without it, nutrients would remain trapped, and ecosystems would stagnate. Each droplet that falls on the forest floor may one day reach the sea, enriched with carbon and minerals from its journey. The rhythm of water's movement sustains not just life, but diversity itself, linking mountains to estuaries in a chain of nourishment as ancient as the world. Clouds seed rain that shapes landscapes over ages. Clouds do not simply float and vanish. Within them, microscopic particles act as seeds around which water vapor condenses. When the droplets grow heavy enough, they fall as rain, feeding rivers that carve valleys, fill lakes, and shape continents. Over millions of years, rainfall sculpts the face of the planet, wearing down mountains and carrying their remains to the sea. It creates fertile plains, nourishes forests, and fills aquifers that support civilizations. Each storm, no matter how brief, participates in this slow transformation. The raindrops that fall on a single hillside today may one day form the soil that grows a forest, centuries from now. Clouds are not only fleeting shapes in the sky, they are builders and sculptors of the earth, weaving together the cycles of air, stone, and life in the patient artistry of erosion and renewal. Water reflects the sky, but also absorbs its own color. When we gaze at a lake or the sea, we often think it looks blue because it mirrors the sky. That is only half the truth. Pure water actually absorbs the red parts of sunlight more effectively than the blue, allowing the cooler tones to scatter back to our eyes. In shallow water, this effect is faint, but as depth increases, the hue deepens into rich azure. Clouds, sediment, and plant life can alter the shade, painting oceans in countless variations of turquoise and green. The color of water is a dialogue between reflection and absorption, between light above and molecules below. It is a subtle chemistry that shapes how we perceive the planet itself. To look into water is to see both the heavens and the material of life intertwined, an image of Earth as seen through its own luminous skin. Deep water appears blue because it absorbs red light. Sunlight entering the sea travels in a slow fade through the spectrum. Red, orange, and yellow wavelengths are absorbed first, leaving blue to dominate the depths. After only a few meters, nearly all warm colors vanish, and by the time light reaches deeper layers, only the faintest blue remains. This is why the ocean seems to glow from within, an inner light filtered through purity and depth. Fish and corals have adapted to this spectral world, developing pigments that thrive in blue environments. Divers who descend far below the surface see their skin and gear turn monochrome, stripped of red hues. The phenomenon reminds us that color is not a fixed property, but a conversation between light and matter. The sea's blueness is a quiet illusion, created by absorption and scattering, a daily miracle where the physics of light becomes the poetry of the deep. Pure water can glow faintly under ultraviolet light. Under ultraviolet illumination, perfectly clean water emits a soft, almost invisible luminescence. This faint glow comes from the interaction between energetic photons and the molecular bonds within the liquid. Impurities, dissolved minerals, or organic matter can change the hue and brightness of this subtle radiance. Scientists use this property to measure purity and detect pollutants. The fluorescence of water is delicate, vanishing as soon as the light is removed, a silent reaction at the quantum level. It reveals how even the simplest substance hides complex behaviors, invisible in ordinary daylight. This gentle glow has practical uses in environmental studies and astrophysics, helping researchers identify water in icy comets and extraterrestrial materials. Beneath the surface of what seems mundane lies a flicker of light, a sign that even still water holds the memory of energy, the faint afterglow of the universe's first illumination. Bioluminescent plankton make ocean waves glow at night. In warm coastal waters, microscopic organisms called dinoflagellates perform a nightly miracle. When disturbed by movement, they release flashes of blue-green light that shimmer across the surface. Each tiny spark is the result of a chemical reaction within their cells, a blend of luciferin and oxygen that converts energy into bioluminescence. The combined effect turns waves into liquid starlight, glowing trails that follow every ripple, fish, or boat. These living lights help deter predators and communicate between individuals, forming one of nature's most mesmerizing spectacles. Beaches that host such displays seem to breathe with light, as though the sea itself were dreaming. The phenomenon occurs all over the world, from tropical lagoons to distant bays, reminding us that life has found ways to paint even the darkest waters. In those glowing tides, we see biology become beauty, chemistry become wonder, and the night itself come alive. Some bays sparkle blue when disturbed by movement. Certain coastal inlets remain calm and dark until a hand, paddle, or passing wave stirs their surface. Then, as if awakened, the water glows with a ghostly blue light. This brilliance comes from dense populations of bioluminescent microorganisms that live in sheltered waters. When disturbed, they emit a brief flash to startle predators, creating a glowing halo around anything that moves. The intensity depends on temperature, salinity, and the abundance of plankton, turning some nights into radiant performances of natural light. The bays of Vieques in Puerto Rico and Luminous Lagoon in Jamaica are famous for their ethereal displays, where every stroke of a swimmer's arm sets the sea ablaze with blue fire. The sight is pure enchantment, a meeting of biology and physics that transforms water into a living lantern, glowing quietly under the stars, as if the ocean were sharing its own slow heartbeat. Water amplifies sound and carries it 4 times faster than air. Sound travels differently through liquids than through gases. Because water molecules are packed closely together, vibrations pass between them much more efficiently, allowing sound to move nearly 4 times faster than it does through air. This makes the underwater world a place of surprising noise, filled with clicks, groans, and sounds that can carry for hundreds of miles. Whales and dolphins rely on this clarity to navigate and communicate across vast distances. Submarines and scientists use it to map the seafloor or listen for earthquakes. Yet this same property also means that underwater environments are easily disturbed by human noise, which can confuse animals that depend on acoustic signals. The speed and reach of sound in water reveal how dense and connected the medium is. Even in darkness, the ocean hears itself, a living network of vibration echoing through its endless, unseen corridors. Whales communicate across entire ocean basins. The songs of whales can travel for thousands of miles beneath the surface. Low-frequency sounds move through deep channels of water with remarkable efficiency, allowing these enormous creatures to remain in contact across oceans. Each species has its own language of pulses, moans, and melodies. Some songs last for hours, repeating complex patterns that may serve to attract mates or coordinate migrations. The precision of these sounds is extraordinary. A blue whale's call can be louder than any machine built by humans, yet it is musical and haunting. Researchers have discovered that whale populations change their songs over time, as if they were composing new variations. The ocean becomes their stage, its density and depth shaping every note. Listening to them is like hearing the voice of the planet itself, vast and resonant, reminding us that communication began long before words were ever spoken. Sound can get trapped in a layer called the deep sound channel. Within the ocean lies a narrow layer where the speed of sound reaches its lowest point. This zone, known to scientists as the deep sound channel, forms where temperature and pressure balance perfectly. Sound entering this layer bends back toward it from above and below, becoming trapped and able to travel extraordinary distances without fading. Whales use this natural corridor to send their calls across basins, and submarines use it to listen in near silence. The discovery of this layer changed how we understand underwater acoustics, revealing that the sea is not an empty space, but an intricate structure that guides sound like an instrument's body. The deep sound channel is a hidden pathway of resonance, carrying the whispers of animals, currents, and storms through darkness, a reminder that even in the deep, sound finds its own kind of horizon. Water pressure increases by 1 atmosphere every 10 meters of depth. The deeper we descend into the ocean, the more the weight of water presses down. For every 10 meters, the pressure increases by the equivalent of Earth's entire atmosphere at sea level. At modest depths, this squeeze is already intense, capable of crushing air pockets and distorting metal. Deep-sea creatures survive only because their bodies contain no trapped gases, their tissues perfectly balanced against the surrounding force. For humans, venturing into such depths requires reinforced vessels built to withstand thousands of tons of pressure. Even a small leak can turn catastrophic. The physics of pressure governs everything that lives or moves beneath the waves. It shapes anatomy, influences chemical reactions, and limits how far life can go. The ocean's depth is not merely a measurement of distance, but of endurance, where matter itself is tested against the quiet, unrelenting weight of the world. The deepest point in the ocean would crush steel. At the bottom of the Mariana Trench, the pressure exceeds 1,000 times that at the surface. A steel sphere would collapse instantly under such weight, yet delicate organisms still survive there. The immense force compresses water slightly, alters sound speed, and even changes how minerals form. Only a few submersibles have ever reached these depths, descending through total darkness where temperatures hover just above freezing. The landscape below is alien, shaped by tectonic forces and covered in fine sediment that never sees sunlight. When explorers switch off their lights, it is the purest blackness imaginable. Still, life persists, proving that biology can adapt even to extremes beyond comprehension. The deepest point is more than a destination. It is a boundary between human exploration and the unknown, a place where the limits of physics meet the quiet persistence of life. Yet microbes thrive in the Mariana Trench. Despite the immense pressure and absence of light, microbial life flourishes at the very bottom of the ocean. These tiny organisms feed on chemical compounds that drift down from above or seep from the crust below. Some can survive conditions that would destroy any surface species, repairing their DNA as it breaks apart under stress. Others metabolize slowly, dividing perhaps only once every few centuries. Their resilience offers clues about how life could exist on other worlds where sunlight never reaches. The communities they form recycle nutrients and maintain balance even in the planet's most inhospitable environment. Each microscopic cell is a triumph of adaptation, thriving where pressure crushes, temperature chills, and darkness reigns. The trench floor, though silent, is alive with invisible purpose, proof that the boundaries we imagine are far narrower than the reach of life itself. Some life forms survive in superheated boiling water. Around volcanic vents and hot springs, certain microorganisms endure temperatures that would destroy nearly all other life. They live in water so hot it boils at the surface, protected only by the immense pressure of their environment. These extremophiles have enzymes and cell walls adapted to high heat, allowing their proteins to remain stable where others unravel. Scientists study them to understand how life might arise in extreme conditions, whether on early Earth or distant planets. The existence of heat-tolerant organisms reshaped biology's definition of habitability. It proved that water, even when near its boiling point, can still nurture life. The same element that cooks and sterilizes can also preserve. Each of these microscopic beings is a reminder that life's strength lies not in comfort, but in adaptation, in the quiet ability to endure when no one expected survival to be possible. Others live inside ice crystals without ever thawing. In the coldest regions of the world, tiny organisms survive frozen within ice, suspended in near timelessness. They inhabit microscopic pockets of liquid brine that remain unfrozen between crystals, drawing faint energy from trapped minerals and sunlight filtered through snow. Some endure for centuries without movement, reawakening when the ice melts. Scientists have revived bacteria from glaciers and permafrost tens of thousands of years old, still viable and capable of growth. These frozen survivors help reveal how life might persist beneath the ice of distant moons like Europa or Enceladus. Even in conditions where metabolism nearly stops, water remains the key to endurance. Within each frozen chamber lies a small, waiting world, a whisper of persistence that turns the idea of stillness into another form of life's slow, patient motion. Water is the only substance found naturally as solid, liquid, and gas on Earth. Among all known materials, only water exists naturally in all three states of matter on our planet. Ice, liquid water, and vapor constantly exchange forms as temperature and pressure shift. This versatility shapes weather, geology, and the conditions for life. The frozen peaks of mountains feed rivers, evaporation builds clouds, and rain renews the land. Without these transitions, Earth would lack seasons, storms, and the gentle balance that allows ecosystems to thrive. The coexistence of all three forms at once makes water an engine of transformation, capable of sculpting continents and sustaining every living cell. No other substance moves so gracefully between stability and change. Its cycle is both physical and poetic, a continual act of renewal that binds the planet's surface, sky, and heart into one harmonious whole. There is more water locked in Earth's mantle than in all the oceans combined. Far beneath our feet, deep within the rocky mantle, lies an enormous hidden reservoir of water, bound within minerals. This water does not flow freely, but exists as hydroxyl groups inside crystal lattices. When these rocks melt or shift, the water can be released as vapor, feeding volcanic eruptions and contributing to the atmosphere. Estimates suggest that the amount stored there could equal or even exceed all the surface oceans. This buried supply plays a crucial role in the planet's geology, influencing tectonic movement and the creation of continents. It acts as a silent regulator of Earth's climate over immense timescales. The discovery of such deep water changed how scientists understand our world. The oceans we see are only part of the picture. Beneath the crust lies an ocean of stone, holding the forgotten moisture of Earth's earliest beginnings. A cloud of water vapor larger than the Milky Way was found in deep space. Astronomers have detected a colossal reservoir of water vapor surrounding a distant quasar, a bright core powered by a supermassive black hole. This cloud spans hundreds of trillions of miles and contains enough water to fill thousands of times all Earth's oceans. The discovery proved that water existed throughout the universe even when it was still young. The radiation from the quasar heats the vapor, causing it to glow faintly in infrared light that telescopes can detect. Finding such an immense concentration of water in deep space suggests that the basic ingredients of life are far more common than once thought. The cosmos, it seems, has been saturated with water since its earliest days. The presence of that vapor across such a vast scale reveals the universe not as dry emptiness, but as a cradle waiting for life to stir. Water might be common throughout the universe. Evidence from comets, interstellar clouds, and exoplanets shows that water is not rare but widespread. Its simple molecular structure forms easily wherever hydrogen and oxygen meet under the right conditions. Astronomers have found it frozen on distant moons, vaporized in nebulae, and flowing on planets far beyond our solar system. Wherever there is heat and chemistry, water appears to follow. It acts as both solvent and stabilizer, enabling complex molecules to assemble. This ubiquity reshapes our search for life, turning it from a local curiosity into a cosmic expectation. When we look to the stars, we now see not emptiness, but potential oceans waiting in the dark. Water's presence across the universe reminds us that the same gentle liquid that falls as rain here may be falling, even now, on worlds we have yet to discover. Without it, carbon chemistry would collapse. All known life depends on the reactions of carbon, but those reactions need a medium in which to unfold. Water provides that medium, allowing molecules to meet, bond, and separate in delicate equilibrium. Its polar nature dissolves a vast range of substances, bringing reactants together while stabilizing them against random destruction. Without this solvent, the chain of chemical interactions that builds proteins, sugars, and DNA could not occur. In essence, water is not only the stage for life's drama, but also one of its central actors. Its ability to moderate temperature, transport nutrients, and shape environments makes it indispensable to any form of complexity. The chemistry of existence itself is written in water's script. To imagine a living world without it is to imagine silence where there should be motion, a universe without the flowing dialogue that gives matter the spark of awareness. Every living thing we know depends on it entirely. From single-celled organisms to forests and whales, every form of life relies on water for survival. It carries nutrients, regulates temperature, and facilitates nearly every chemical reaction that sustains metabolism. Cells are mostly water, their membranes shaped to control its movement. Plants draw it upward against gravity animals drink, absorb, and exhale it continually. Even dormant seeds hold a trace, waiting for moisture to awaken them. The boundaries between living and non-living blur when water is present, for it animates what would otherwise remain still. Across ecosystems, it links predator and prey, root and sky, death and rebirth. Remove water, and everything collapses into dust. Its constancy connects all biology into one global organism, endlessly cycling through breath, blood, and rain. In every heartbeat, every green leaf, and every wave, water performs the same essential act, the quiet continuation of life. To drink water is to taste the memory of stars. The atoms that form a sip of water were forged in ancient fires. Hydrogen was born in the first seconds after the universe began, and oxygen came from dying stars that exploded, scattering their elements across space. When those atoms met, they joined to create the molecule that would cradle life. Each glass you raise is therefore a reunion of cosmic history. You are not just quenching thirst, you are taking part in the oldest cycle of all, connecting your body to galaxies and time itself. Every drop holds within it the remnants of creation, the ash and light of the cosmos condensed into clarity. To drink is to participate in the universe remembering itself, a moment of communion between stars and life, between the infinite and the intimate, between what once burned and what now breathes. Somewhere, perhaps not far from where you are now, a single drop of water falls. It may strike the surface of a pond, or the curve of a leaf, or the open sea. And from that sound, small, round, vanishing almost as it begins, the story continues. The same drop may one day rise as mist, drift across mountains, and fall again as rain. It may freeze, melt, and freeze once more. It may travel through rivers, clouds, oceans, or you. Each transformation is a quiet echo of creation itself, a rhythm that began before the world took shape. Water is patience. It wears down mountains and polishes stone. It holds the sky in its reflection and carries sunlight into the depths. It remembers nothing, yet it connects everything. It is the pulse in every tide, the shimmer in every storm, and the calm that follows. So as you rest now, imagine yourself floating within that endless cycle, a drifting molecule in a cosmic sea of change. The motion slows, the surface smooths, the breath deepens. If you enjoyed this quiet journey, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the deep waters cradle your thoughts, slow, weightless, and free. Good night.